In this lesson, we shall focus on linear algebra, and the module code is the MAM2000 W2LA. Okay, obviously we shall be looking at a wide range of past exam papers, and we decided to work on these papers beginning from the most recent to much older past papers. Okay, we shall do a lot of them. Okay, and also the theoretical concepts will as well be covered. But let's take a look at what was said recently so that we can sort of set the pace using it.
Okay.
Right. To just have a discussion about one question that is very interesting, but also very, very straightforward. It's a question that says, let A be the given matrix of the given size. How many rows? 1, 2,
1, 2, 3.
4, 5. 5 rows. How many columns? 2, 4, 6 columns. So
6.
this one is a 5 by 6 matrix in size. And the matrix U is this matrix here, which is an upper triangular matrix, okay? So now you can see the transformation of the matrix A to an upper triangular matrix. Now the matrix U is a row echelon form of the matrix A. Very interesting. So in other words, the examiner is saying that the matrix A has actually undergone row reduction to row echelon form, right? And you did not check this. Okay, it's a lot of work. The examiner was very, very kind and generous. If anyone would expect students to row reduce these to this in the exam of the size 5 by 6, it's not realistic. I mean, that would be very crazy, very, very unkind.
Yes.
It's so big, it's so big, it's so time consuming, and there's always a greater chance of making mistakes here. Okay, but they are saying you need not check this. Okay, use this information to answer the following questions. Right, let's use this information given a basis. Rather give a basis for the row space of the matrix A, and we shall also look at the column space of the matrix A. You need not give reasons for your answers. Okay, first things first, let us look at the row space of the matrix A. So now the matrix A has been obviously row reduced, and now if we're to look at the row space of the matrix, we need to focus on the non-zero matrix. So we shall focus on this row, that one, these, that, and those are the four non-zero rows. The zero row itself will be out of the picture. Why? Because the zero row is actually, we're looking at the row space, and the row space consists of the non-zero rows, because the non-zero rows themselves are essentially the linearly independent rows, and this zero row is a linearly dependent row. So this one is linearly dependent. Okay, so
why is it linearly dependent again?
Okay, all right. It is linearly dependent because of the fact that it is actually consisting entirely of zeros. And now the zero vector, so this is sort of the zero vector. So if you write it out, 2, 4, 6 zeros. So the zero vector would be, and obviously you can write it with commas. Right, so you have 0, 0, 0, 2, 4, 6, right, 2, 4, 2, 4, 5, 6. Right, obviously writing it like that, you're able to see clearly that this particular row is actually the zero row all the time. It is linearly dependent because if you want to check this, if you multiply it with a zero scalar and you equate it to 0, you'll always be able to see that it's like saying these times this zero vector with 6 entries, 2, 4, 6 entries, this is 0. If this is 0, then what do you do? If you're multiplying a scalar, because you take a scalar that is in the real numbers, and now if multiplying a scalar by that, it will be a times 0 A times 0, and so on. And then we have A times 0 equals 0. And then we're back to school now, back to high school to then say A times 0 equals 0. What is A? Okay, for
Any
linear
number.
independence, is any real number. So now, because it's any real number, then it means that it is linearly dependent, because we can choose a non-zero number. Okay, because linear independence, which is what we want in the row space, would require that the scalar A is 0. But this one becomes any number, and therefore it is linearly dependent, and hence we discard it. Okay, so now what is then the row space of A? So we then say, but we need to give what we call the basis of this. So in the first Roman figure, so we note that actually a basis, right, a basis for the row space of A will consist of the entirely of the non-zero rows. What are the non-zero rows? 1,
3,
minus 2,
the
4,
first one.
0, the first row. Right. And obviously, then you have the next one, which is 0, 0, 2, 4, minus 3, 3, which is the second row. Next, we are proceeding to the third row, and the third row is the 0, 3 zeros, 1, 3, 7. Okay, and then we have 2, 4, 5, and then now 2, 4 zeros, 5, and then at the number 5. So now this obviously becomes a basis for the row space of A. Like it says that it is a basis, because a student can come and take this, or in which case, because after you've done the row reduction, you can say that is the answer, or you can say the row space of A. And once again, this is not only limited to this. So you can take one, you can take this one, because these are row equivalent. Right, so you can take 1, 3, 1, minus 2, 4, 0 is also correct. 1, 3, 3, 2, 1, 3, 2, 6, 4, 1, 8, 10. Right, is the third one, and then now you have the fourth one, 3, 9, 7, 2, 6, 11. So this is sort of what we have. So these are not the only ones, because we're saying a basis. So in which case, therefore, you can have another one. Like you can decide to multiply this one by any number, so because it's a this is a basis, in which case if we can multiply this by any number, like multiply by 2 here, multiply by 3 there, multiply by 4 there, and these are multiples actually of these given vectors, which will also form another basis. So there are actually obviously many bases here that are acceptable. And once again, you need not give reasons for your answer, and the marks are actually 2 there. And we proceed now to determine the next question, to solve the next one. And in the next case, we're interested in the column space. Similarly, now in the column space, you actually focus on the linearly independent columns, right? So now, which columns are linearly independent? So we focus on now we are interested in this. So we're looking for what we call the linearly independent. Yes, the linearly independent columns. Right, linearly independent columns of A. What are the linearly independent columns of A? Are those that are not multiples of each other, yet they are not 0. So in this case, it will be this one. But this and that are multiples of each other, because we have 1 here and you have the number 3 there, and they appear in the same row. So in which case, it's just like this one multiplied by 3. If you take this vector and multiply this vector by 3, you'll get this one. So these are the same vector. Okay. So now you must pick one of them. Right. So you can either pick this one or that one. We preferably pick the first one. Okay.
Yeah.
Now next, this one is okay because this must be in row echelon. In row echelon form, it means you must have a one there. And then this one here is having the one in the echelon position. So we're going to take this one here. And here is this one here that is also doing a very interesting job. It is in the next sort of echelon position. So you're going to take this one here. Now, if you look at that, so we have taken 1, we have taken 2, we have taken 3, right? And then now, if you check very carefully, this one also, it's actually just a multiple of this one, because if it is not, then this one must be in a lower position, but the 3 is not in a lower position. So in this case, therefore, we can see that 5 is actually in a lower position, meaning that because these are in equivalent positions, it is possible that surely these are actually row equivalent. By row reduction, this vector can be transformed into this. So and then because of that, then we're going to take this one as our fourth vector. So we therefore have those particular 4 vectors then, and we discard this vector out. We also discard this vector out. Why? Because these vectors are multiples of already chosen vectors. And now for linear independence, we require that the vectors must be distinct vectors. The vectors should not be a vector we put in the basis, cannot be a multiple of another vector in the basis. Otherwise, then it means we're repeating there. Okay, so we are putting the same vector twice in a set. We do not repeat numbers in mathematics. So as a consequence there, we then say a basis. So we're looking at now the solution to a second Roman figure. Right, a second Roman figure. Yes.
Can I say that we take every row, every column that has a pivot on it?
Yes, definitely. We take those columns that certainly are pivoted columns that contain pivots. Those are the columns we take, and the others we do not take because obviously they are multiples of the ones that have pivot or sort of called the pivot columns. Right, in which case, therefore, a basis, we then say a basis for the column space is, okay? So let us look at the basis for the column space. So we're going to take the first one, right? Like I said, that we can either put this column or you can put the corresponding column in the original matrix A, which is what we're going to do, right? So at this point, you can take and put this one here. You can put 1, 1, 2, 3, 4. Okay, so you can put, yes.
So are you saying that I can also put the
1, 0, 0?
Yeah.
Yes. Okay,
No,
so
but I read. Okay.
please come
So
again.
when I was reading my notes, it said that we can't take the row reduced one. We can only take from the original matrix when it comes to the column space, the basis
Well,
of the column
yeah,
space.
definitely. Yeah, of course, because anyway, they are row equivalent. Okay, because of the row equivalence, they're isomorphic. So in which case, therefore, you have that choice. But again, the best ones to take are the original entries anyway. So, well, I hear you there. But the best entries to take are the original because these ones, this is a row reduced matrix. In which case, therefore, anyone can obtain their own. Like I said, that every student can get their own, and taking these columns on these rows is not advisable. The best is to take the original ones. Why? Because that's the matrix that was given. To avoid confusion. Well, I hear you there. So in which case, therefore, we would say, because there's what we call isomorphism in mathematics. So these things become isomorphic, in which case, therefore, they're isomorphic spaces. But for simplicity, just take the original. Okay, so in which case, therefore, you take the 1, 1, 2,
And then the third one.
3, 4. And then now, because it's the same as the second, so you take the third one. So you're going to take this one. So you're going to take the, what is it? The 1, 3?
Row 3.
4, yes, 4, 7, 10. And then?
Row 4.
And then, right, so yeah, we took this one, and then we take this one here, the fourth column. So we're going to take this one here. Okay, we're going to take this one here, which is exactly minus 2, 2, 1, 2, 4. Next, there is
the last
one more, the very last, which is 0, 3, 10, 11, 14. Once again, as I said already, these are row equivalent. Because the question says a basis. What about if a student takes another one and now they've multiplied this one by 2 here? Well,
isn't it
obviously,
the same because they're row equivalent?
Because of the row equivalence. So, or in this case, you can even speak of what you call column equivalence. Okay, but anyhow, it's best to just take the original vectors themselves to avoid issues here. Okay, to avoid issues. Okay, right. So we have got the answer there. We've got the result. We've got the result. So this is exactly A, and this is therefore the answer. I'm hoping that it is very clear and right, it can be written like this. And it is the most acceptable answer to the question. We proceed. It's clear, is that correct? Okay.
Yes.
Okay, good things. Right, now once again, it's good to just take the original entries themselves. Okay, the original columns. Okay, so we continue. We continue. Okay, the next question is about the nullity. Right, so obviously, I mean, we're given the matrix A and the matrix U, which is the row echelon form of the matrix A. You need not check this. Use this information to answer the following questions. Give the rank and nullity of A. Give the rank and nullity of A. So obviously, the rank of A. First, we speak about the rank of A. Right, so what do we define as the rank of A? Well, the rank of A is the set spanned by the by the rows. Okay, by the rows. So now at this point, you count the number of the non-zero rows of A. So in other words, now want to find the rank. Right, the rank of the matrix A, and let's count 1, 2, 3, 4. You counted 4, right?
Yeah.
Okay, so you mean the rank of A is 4 because there are 4 non-zero rows there. What is the nullity of the matrix? So you go on to then say the rank, right? Something called the rank of A plus the nullity. Plus the nullity of A is always equal to the number of the columns of the matrix A. 2, 4, 6. Okay, so the rank plus the nullity is a theorem. The rank plus the nullity equals the number of the columns of the matrix A, and therefore at this point we know very well that the rank of A is the number of the non-zero rows, which is 4, plus the nullity. All right, plus the nullity of the matrix A, and this equals 6, which means therefore you have the nullity. The nullity of the matrix A would therefore become exactly 6 minus 4, and 6 minus 4 is actually 2. So that the nullity of A equals 2. Okay, so obviously we're able to see therefore that the rank of A equals 4 and the nullity of A is actually 2. We're able to see that the nullity of A is actually exactly 2. Why? Because we're able to see therefore that at this point we have exactly 4 plus 2 equals 6. Okay, but by noting that the rank is 4 because of the 4 non-zero rows, we are able to see that the nullity itself is actually what? Is actually 2 there. Okay, so we're good by using that theorem there. Next question. Right. Okay, next we actually now look for the nullity of the transpose. Right, so obviously, this one is straightforward in the same way. One way to do this for the nullity, you would then say, okay, the rank, it's easy. You can just say the rank. Right, so you can say the rank of A transpose plus the nullity. Okay, so you switch the columns and the rows around. Okay, so the rank of the matrix A transpose plus the nullity of the A transpose equals the number of columns of the transpose. 2, 4, 5. 5 by 6 is the size of the matrix A, or even the U is the same size. Okay. Now, if you speak about, so now if this is the matrix A, we're going to speak about A transpose, which is going to be the other way around. Okay.
6 times 5.
So yeah, it becomes 6 by 5. So now at this point, we're interested in finding the number of the columns here, and the number of the columns is 5 for this. So now at this point, you're able to see therefore that you need to put 5 here, because now we're then saying the rank of A transpose plus the nullity of the A transpose equals the number of the columns of the transpose of A, and therefore the number of the columns is 5. Okay, good. And obviously we're able to even see, without even having to write this, that when take the transpose, the columns become rows. Okay, in which case, because of that, then you have that you have the number of the columns there, which actually equal to 5. Okay, good. All right, so we continue then. All right. So we continue then. Okay, next. Okay, there are certain things that are much easier for us to get, like our rank here. It's very, very straightforward. The rank of the A transpose is going to be what? So the rank of the A transpose can be seen as the rank of the U transpose, right? So if you look at the U transpose, how many rows will these U have? How many non-zero rows will these actually be able to have? So in other words, you will take this column. Okay, let's look at, let's write down here. Right, yes. So if you look at the U transpose, to be 2, 4. So 1, 2. Okay, so if you just take the U transpose, we're just experimenting anyhow. Right, so that this column becomes a row, and this column also becomes a row. We have 2, 4. Right, and then also this column becomes a row. 1, 2, 1, 2, 3. Right, and then this column becomes a row. Minus 2, 4, 1, 1, 2. This column becomes a row. 4 minus 3, 3, 0, 0. This column becomes a row. You have 0, 3, 7, 5, 0. Okay, so this is exactly then what we have here. Okay, now let us focus on this matrix, obviously, because we're looking at A transpose. We want to determine the rank of this, but obviously with the rank, we actually focus on the non-zero rows. Okay, so in other words, how many non-zero rows are there? Right, so
6.
Okay, that's very interesting. Yes, you're counting exactly 2, 4, 6. But because this is a multiple of this, right? Because this is a multiple of this, So in other words, these are like one row, because you can row reduce this one to, you can row reduce this one to, the one is going to become a 0. Okay.
Okay.
So
Yeah.
now you also now proceed to then examine right, that this at this point is in the next position, this, and also if you look very carefully, these two, right, these two themselves are such that if you look very carefully, can you be in a position to get zeros here? This entry can help us to get zeros there. This you can have actually get zeros there. So in other words, we will focus on the next position like that. Right. So at this point, then you are able to look very carefully and determine that how many. Now we have 2, 4, 6 rows. Right. And therefore, if there are 6 rows there, then the question becomes, what then will the rank be of the transpose? Right. So we're able to see, but also simultaneously, how many columns are there? So you'll count exactly 4. Right. So you'll count exactly 4, because this is like one row, and then 2, and then these 2 form 3, and then 4. Okay, because ones you count them as 1. Why? Because you can row reduce this and say this minus 3 of this to make this 0. Okay, and these ones, row reduction is going to prove that these are equivalent. You can take one of them. Okay, so as a consequence, then this is just 1, 2, 3 with these 2, and then 4. So in other words, we're able to therefore see that if you then say we have the rank of A transpose plus the nullity of A transpose equals 5. Therefore, this means that here at this point, you would therefore have that the rank itself, we've already seen that it is 4. Okay, because these and that have the same rank. They have the same rank. It means that even the rows themselves are row equivalent. If the rows are row equivalent, you can take either this row or that row. They are row equivalent. But as said already, you have that choice. Right. So at this point, then you have exactly plus. Right. So you have exactly plus the nullity. Right. Of the A transpose equals 5, which means therefore the nullity. Right. The nullity of A transpose therefore equals 5 minus 4, and 5 minus 4, it's a 1. It's a 1. It's a 1. So now it means therefore the nullity of the A transpose equals exactly 1. Okay, so that's certainly correct. That most certainly correct thing. So yeah, we have discussed that, and we're trying to just discuss. Okay, the theorem we used here is rank plus nullity of a given matrix equals the number of columns of the given matrix. Okay, we're good. Now we proceed to do the next question. The next question. We proceed to do the next question. Right, in the next case, we're still having the same information. We're saying, is it true that for every vector V in R5, there is a U in R6? Because you have 2, 4, 5 by 6. Is it true that for every vector V in R5, there is a U in R6 such that V equals AU? Obviously, we examine that and we attempt to give a reason for the answer. So this obviously is a notion that is even linked to the sort of transformations that are involved here. And so we shall relate these very closely to the notion of transformations. Why? Because every matrix can be associated with a linear transformation that generates the matrix. So given a matrix, you can always find an associated linear transformation or map that associated with that given matrix there. So at this point, we actually will be able to see a couple of things because the examiner was using a play on words and also was playing with the dimensions of the respective column and row vectors there. So obviously at this point, if you look very carefully, you'll be able to see that we need to actually examine the basis for the, right, so we note that. Right, we note that the dimension of the column space of A. I want us to examine the dimension of the column space of A because we've already got the dimension of the column space of A. According to dimension is the number of elements in the basis, right, of the column space of A. But now we have saw that in the column space of A, dimension is what? Is exactly 4. Well done. Right. And the dimension of the R space. Yes, of the row space, of the Euclidean space of the 5th dimension, that is the dimension of R5. Right. Well, the dimension of R5 is 5. Okay, like the dimension of Rn is always, the right dimension of Rn is always n for any integer. Okay.
Oh yes.
Yeah, for any for any counting number. Okay, so right, we know that at this point the dimension of the column space is 4. We saw that. And now, because why have we been mentioning these things here? We are mentioning these things because of the fact that we take note of the notion of the fact that the matrix A itself is a matrix with 2, 4, 5 rows. So it has 5 rows. Right, so the matrix A has 5 rows and 6 columns. And obviously the same applies to the matrix U as well. It is actually of the size that is given. Okay, so we note therefore that the dimension of the column space of A is actually 4. And the dimension of R5, which relates to the rows. Right, so at this point, we realize that dimension of the R5 itself is actually 5. Why? Because we're saying for every V in R5, so obviously we are actually looking at any vector in R5 if this is possible, right? And we can be able to, can we be able to take a U in R6? Right, and obviously at this point, R6 at this point is to do with the vector space from which we're able to take the columns, because we have 6 columns here. And therefore, the dimension of the column space we saw that is 4. So it is actually, therefore, we can see that as much as U itself comes from R6, but the dimension of the column space is 4. Meaning this is not an ideal situation for what the examiner is playing here, because there are 2, 4, 6 columns. There are 6 columns. Okay, there are 6 columns. But now the dimension of the column space is what? Is 4. So it's 2 less. It is 2 less. And therefore, because it is 2 less, but also we're able to see that this one here, the dimension of the R5 we're dealing with is exactly 5. Okay, what is then the implication of this here? What is then the implication of this? To say that at this point, let us look at what is happening here. Because if you then say V equals AU, what is the size? Where is this V living? Where does this V stay? Okay, V stays in R5. Okay, so in other words, this V itself, it's going to be in R5, it's going to be A1, A2, A3, A4, A5. Can write it like this. We can write it like this. Okay, right. We can write it like this. Okay, and then now, okay, so this is V because it is there. Right. So you continue. Okay, we continue. Why? By just a minute, please.
Okay.
Right, just a minute. Right. Wondering, I actually tempered with something. Okay, never mind. Okay, now we're right back. Right, so at this point then, what are we then saying? Okay, we are looking at the fact that the column space itself, there are 6 columns, but you can see dimension of the column space is less than that. But also we are looking at the fact that, let us analyze this together. What is the size of the matrix A here? Okay, we've already written that one, but I want us to analyze. It's 5 by 6. So the matrix A is a size 5 by 6. And this one, what is the size of V? It is 5 by 1. Okay, so if it's 5 by 1, this one here, what must the size of the U be? It must be 6 by 1.
6 by 1.
Right, it must be 6 by 1, like this. So obviously we agree, therefore, that U itself lives in this vector space. It lives in R6, where we have the 6 by 1 vectors. Okay, but what is then the problem with this claim? That for every vector in R5, we can always get a U in R6, such that this equation is always true. Well, we actually able to see the deficiency here, and the deficiency, that dimension of the column space becomes 4, and this makes it false. Okay, so we know that dimension of the column space is 4, as much as that of the of R5. Okay, of R5 itself, which associated with the row space, right, is actually a 5 because of the 5 there, and these are 6 there. We're able to therefore see that because of one deficiency, the dimension of the column space is obviously less than the actual number of the columns there. So it is not the case. So we know that this dimension is 4 and that dimension is 5. So that, right, so that it is not true. Right, it is not true. Right, it is not true that for every. It's not true that for every V in R5, there is U in R6, such that, right, such that V itself, vector V, is AU. Right. Well, thus we can say that not every vector, right, thus not every vector can actually be written in the way the examiner is claiming. That thus not every vector, right? Thus not every vector, right, can be expressed. Not every vector can be expressed as a linear combination. Linear combination of columns in A. So this is exactly what we have. This is then exactly what we have. Yeah, any question?
Can you go over it again?
All right, so obviously at this point, we're trying to analyze this and look at whether the claim by the examiner is always true. What is the claim here? The claim is that, well, it is a question that the examiner is asking to say, is it true that for every vector in R5, vector V in R5, there exists a vector U in R6? So the examiner was looking at the size of the matrix A, and the fact that for every vector V in R5, is it true that you could always find a vector in R6 such that V is equal to a U? Okay, this is the question. V equals a U. Is this true or not? So the examiner was looking at the fact that A itself is 5 by 6. And if A itself is 5 by 6, we can always be interested in really saying, can we take the matrix A, multiply it by some vector? Obviously, because if we multiply A by any given vector, how many columns does A have? It has six columns, so it means that A itself must have the number of rows of A must be the same as the number of columns of A. For the number of rows here must be the same as the number of columns. So these numbers must be the same, right? So obviously we require that U be coming from the set of vectors that is going to be compatible for multiplication to actually be possible here. So U must be from 6 by 1 vectors, and it's R6, such that if you perform this product, you're able to get always a vector in the 5 by 1 space or in R5. Is this always true? I mean, that is the question. So first and foremost, we need to analyze a couple of things that at this point, what are we actually able to see here? We actually focus on the fact that the column space of A becomes key in our analysis, because we are interested in saying we can always get, there is a U. Can we always be able to get a U that does this job? Right. So can we be able to get a U that is in R6 that does this job? So the columns themselves, are they enough? Well, put differently or in another form, is to then say, are the columns all linearly independent? Well, obviously, these columns are not entirely all linearly independent. Why? Because the dimension of the column space is actually less than the number of the columns. Okay, because it is less than the number of the columns, it's actually indicative of the fact that, therefore, there is a deficiency. The dimension of the column space is actually less than 6. If the dimension of the column space is less than 6, it means, therefore, that it is not true that for every V we can always get a U in R6 such that this equation is possible. And because of this observation, because why? Why are we even mentioning dimension of the column space here? Because U itself is such that it is a 6 by 1, which is such that it is actually taking its size from the number of the columns of A for the product to be a possible product. And thus, obviously, not every vector can be expressed as a linear combination of the columns in A. Right. Not every vector can be expressed as a linear combination of the columns in A. Okay, so this is what we're saying. Thus, not every vector can be expressed as a linear combination of the columns in A. Because we are saying, can every vector V be written as a linear combination of the columns in A? Obviously not. Because the dimension of the column space is less than 6. If it was, if the dimension of the column space was 6, it would mean that every vector can be written or expressed as a linear combination of the columns in A. And this expression would therefore be a unique expression if the dimension of the column space was equal to 6, but it is not. Okay, so obviously, because it is less, therefore it means therefore we cannot have this unique expression. Okay, right. It means therefore we cannot have this unique expression. All right.
Okay,
Okay, we continue.
Can you also is it
Yes.
also possible to explain this in terms of the dimension of the row space?
That's a good question. Yes, definitely. We can always be in a position to explain it in terms of the dimension of the row space. Right.
Okay.
But why is the column space so important and so obvious in making this fact very clear? Well, it's because V itself is a column vector. Okay, so because
How
V
do you
itself,
see that?
okay, how do we see that? Okay, that's a good question. So let us look at what is happening here, for example. We are taking this V, and V is in R5.
R5.
So it is A1, A2, up to A5, right? A3,
Yes.
A4, A5. So that is one way of writing it. Well, we can write it as a row vector as well. Right. Okay, we continue. All right, so this is how we can write V. Now, if we can write V like this, okay, I feel like we can write it like with the V's inside so that we don't get confused. Because now, yeah, okay, you can write with small V's like V1, V2, V3, V4, V5. So it has like V entries that are V. Okay, V1, V2, etc. Okay, now we take the matrix A. Okay, we take the matrix A, and the matrix A. Okay, we are looking at the fact that you're looking at the claim by the examiner. V is AU. So you then have 1, 1, 2, 3, 4, 3, 3, 6, 9, 12, 1, 3, 4, 7, 10, minus 2, 2, 1, 2, 4, 0, 3, 10, 11, 14. Okay, just trying to write the matrix A. I know I've congested the entries here. Okay, now we take U that has the same number of, for the matrix product to be possible. U is in R6 anyway. The examiner made life much easier for us. So we can call the U is going to be having U1, U2, U3, U4, U5, and then U6. Why is it up to 6, this U? Because it is actually such that for the matrix product to be possible, the number of rows here, you need this one to be 6 by 1 because the A is 5 by 6. And these numbers must be the same size. Okay, right. So we have this. So this expression itself is such that if you actually therefore continue to perform therefore the multiplication, how do we therefore perform multiplication of this matrix here? So because this one it's a column vector, right? And we're able to see here 2, 4, 5. How would one multiply this matrix with that? Right, so to multiply this matrix with that, with this particular vector, you will do row by column multiplication. But how else can you multiply these here? Is it the only way to multiply these or not? Well, obviously, if you look very carefully, in terms of variables, you can multiply these and can write these. Let me just multiply these. So if you multiply row by column, so you're gonna say U1 plus, right? So because you multiply according to this, what is the size of the result? Okay, so it's gonna be 5 by 1.
5 by.
Yeah, good. It's gonna be 5 by 1. Right. So if it is 5 by 1, how would you multiply? You multiply these by that. Okay, so if you multiply these by that, you multiply 1 by U1. It's U1, and then you continue with the multiplication. But there's something I want to show here. Okay, because then you can perform another factorization that is gonna make these column vectors, this column, to be a linear combination of columns. Okay, so in other words, if you have 1 times U1, okay, and then plus 3 times U2, plus, is this by this, okay, U3, and then, and this one is what? Okay, 2, 4.
-2, 4.
Yes, yes, okay, I missed something. I missed something here. Yes, I missed something. I missed something. What did I miss?
You didn't.
I didn't miss anything. 2, 4, 6, 2.
Oh, you missed a column.
I missed the column.
column.
Yes, yeah, it's a column I missed. So, let me see, 0, 3, 10. I missed the second last.
The second last.
Yes, second last. Okay, thank you so much. Right, so you have 4, 1, 8, 6, 7. Then you have 0, 3, 10, 11, 14, like this. Okay, good. Now, I'm just saying we're multiplying 1. I want to explain the column factorization here. Okay, so that the column space becomes the most obvious to deal with. Right, so if you're dealing with column vectors, you multiply this. Okay, this is the 1 by U3, then minus 2 U4, and then 4 U5, and then 0 U6. Okay, just something like that. Yeah, okay.
Yes.
Yeah, which is 0. Okay, so we just multiply this row by this column. Right, and obviously you continue with the multiplication process. Let me just do one more. I'm not going to do all of them. Right, if you multiply this one
by the last one.
Okay, yeah, that's good. You can do the last one because I just want to explain the concept. Right, if you multiply this by that, you'd have, for instance, like 4U1 plus 12 U2, and then 10 U3, and then 4 U4, 7 U5,
and then
14 U6. Okay, you get the point like that. Okay. Okay, so we missed some other intermediate intermediate rows in the middle. Now, if you look at this very carefully, what then are we able to get here? Okay, we're able to see that these things here can be written differently. So you can write like this. So this one you can write 1, 4, U1 plus. And then the U2 you can write 3. And the others in the middle here, and then you go to 12.
Yes.
Okay, and then you have U2 that is going to come here. Okay, but now what we're then effectively trying to explain through this presentation is that even to multiply this matrix with that, you can just obviously be in a position to just simply take this column and multiply it by U1. Take this whole column and multiply it by U2. Take this whole column, multiply by U3. So this will be another way to multiply the whole thing. But this presentation is able to tell us that if we're then saying that, is it true that for every vector U, okay, if it is true that for every vector U in R5, okay, right, then all these vectors, all these columns must be right. So all these columns must be what? They must be such that
Must be non-zero.
they must be non-zero. You get the point?
Yeah.
They must be non-zero.
Yes, I get it now.
Because that is the basis for a unique presentation. In linear algebra, we say a vector can be written as a linear combination of others if the rest of the other vectors are non-zero, are linearly independent.
Yes, they must be linearly independent, but we can't in this case because they are linearly dependent.
Yes, there are vectors that are sort of defective, which are multiples of the other, and therefore, because of that, this expression is not going to be possible.
It's not possible. Okay, no, it makes sense.
Yes, because of that. So, but to explain this, we resorted to the notion of the column space. We looked at the fact that dimension of the column space. Why? Because the columns themselves were key because we're studying columns here. And it is the columns that yield are necessary for us to then say we take the columns, we add them up, we get one column vector, V. Okay, and these columns must be non-zero, but also these columns must be linearly independent columns. Okay, so yeah, so that is something that is very important. That is something that is very important. So we continue then to check the next thing. We continue to check the next thing. Right. Let us see the next point, the next question. Right, the next question is very, very interesting. Let us take a look at the next question. Let me see that we have obviously not jammed any question. We actually, let me see. Right. That is fine. That is okay. That is okay. That is okay. Right. So, okay, let us look at this question. Right. So we let A be this 3 by 3 matrix. Find all the eigenvalues of A. So now the eigenvalues of A are very, very straightforward. To find eigenvalues of A, we use the fact that the matrix A minus lambda I 3. And we use this notation. And this we equate to 0. At this point, we would then be in a position to then say, we find the determinant of the matrix A, which is a 6, 0, 0, 2, 0, 1, 0, 0, 2, minus lambda 1, 0, 0. The I3 contains zeros with ones along the main diagonal, which is actually 0 there, like that. And we then continue to analyze these and then say, what then we have here is the following. Right, so we have exactly this one here. Right, so we go down like this. So this would actually be exactly 6 minus lambda. 0, 0, 0. Okay, then we have 2. Right, so we also continue to look at the next thing. Right. Okay. So we continue. We continue. Okay, right. So let us make sure that we have the correct ordering here and we have correct things here. Okay, because we have 6 minus that. And then now for this one, it's going to be like 2 minus 0. And then this one is going to be 0 minus lambda. So it's like minus lambda.
Minus lambda.
Yeah, good.
And then 1.
This one is going to be just 1. Well done. Next, this
And
one is going to be 0 minus 0. This one is
0
0 minus 0. And this one is 2 minus lambda. Like,
yes.
okay, good. Right, so we can decide to expand along any row, any column. So we using cofactor expansion. Right, so we using cofactor expansion. All right, okay, we're gonna take this this first row here.
Yes.
Okay, if you expand along the first row, it's gonna be 6 minus lambda, then we're gonna block this column in this row, then we're left with minus lambda 1, 0, 2 minus lambda. Right, and then obviously now we can have minus 0.
We're just gonna have zeros.
We're just gonna have zeros, so we can just even leave that out.
Yeah.
But let's just write. Okay, because it's
Yeah,
gonna
you
be
can
0
just write
times.
0.
Yes, we can just
0,
write 0. Well done. We can just write 0. I'm happy that you're able to see that. So we can just write 0 because this one is going to be 0 times whatever. So it's going to be minus 0. And this one is going to be
0, and the last one
whatever.
is
It's going to
0.
be plus 0. And the result must be 0 here. Okay, good. It's equal to 0 here. So now at this point, you multiply this and you subtract this. So this times that. So it's going to be 6 minus lambda, which is 2 minus lambda equals 0, which means lambda equals 6. Lambda equals 0. Lambda equals 2. Okay, so these are the actual eigenvalues. So the eigenvalues are actually exactly this one. So you can continue to then say, hence the eigenvalues. All right, hence the eigenvalues. Right, hence the eigenvalues are lambda equals 0, lambda equals 2, lambda equals exactly 6, like so. Right, so we continue right now to check carefully and solve the next thing. Right, so we solve the next problem. Right, this is done on the eigenvalues of the matrix A. Okay, so now, can A be written as a product of elementary matrices? Give a reason for your answer using only your answer in A. Right, so obviously, there are a couple of ways to analyze that. And the one of the ways to look at that is is the matrix A invertible. Okay, so
no, it's not.
okay, yes, so it's not, right? Now, because the
Yes,
matrix A itself is not invertible, why would you think the matrix A is not invertible? Anyway, never mind that.
because of the, I think
Yes,
because of the middle row.
yes. There are
It
many
has a
reasons. There are
0.
many reasons. Lambda
Yeah.
equals, there are many reasons, okay. Lambda equals 0 is an eigen, that's one of the reasons, but which I'll state others.
Oh, okay.
Lambda equals 0 is an eigenvalue, right, is an eigenvalue, is an eigenvalue of A,
Of A.
right. And because lambda equals 0 is an eigenvalue of A, we then say, hence A is singular. Right, it's singular, and therefore
It cannot be written
yes,
as a product of elementary
elementary
matrices.
matrices.
Okay.
Right, good, and therefore cannot be written. Right, cannot be written as a product of elementary of elementary matrices. Cannot be written as a product of elementary matrices. So lambda equals 0 is an eigenvalue of A, hence A is singular and therefore cannot be written as a product of elementary. Obviously, I mean, the question was use only your answer to A. So we have to use the idea of eigenvalues. But I mean, there are many reasons, but eigenvalues were key because we had to use only our answer to A and not other things.
So what are,
Please come again.
yeah, what are the other reasons? What are the other reasons?
Yes, other reasons would be, for example, but obviously different from using A, would be the fact that the determinant of the matrix, one way, is to say the determinant of the matrix is 0.
Yes.
Okay, because now if you find the determinant, you expand for this entry here. If you expand, you cover this column and this row, you multiply this by that. 0 by 2, it's 0. Minus 0 by 1, it's 0.
Yes.
This one is going to be 0 times whatever, and this is going to be 0 times whatever. So because now the determinant of the matrix A, right, the determinant of the matrix A is 0, it means that A is singular.
Yes.
Or has no inverse. Okay, and any other reason will pretty much be very equivalent to that. I mean, alternatively, a student can then say, I want to find the inverse of the matrix A to prove that. Another student can take the matrix A and say, I want to row reduce it. Because if you're able to row reduce it to 1, 0, 0, 0, 1, 0, 0, 0, 1.
0, 0, 0.
Okay. Okay. If this matrix, if a matrix can be reduced to what we call the identity matrix, then the matrix itself is non-singular. It's invertible. You get the point. So I mean, but this would be a lot of work to. The determinant would have been a much easier one in this question, but it's just that we've already done the eigenvalues, and the examiner said just use the eigenvalues. And particularly, the examiner was particular about this. Said use only your answer to A to do this question. Please do not do other things, because I'm sure the examiner was very aware that there are many ways to do this question. And many students would actually find a way to just answer these and say, we just need to look at the singularity. You know, if this matrix is singular or not. And we can use determinants, we can use arguments around the existence of the inverse of the matrix A. Okay, we'll look at the next question. Right, so...
Okay, so it's only...
Yes.
It's only singular if there is an eigenvalue of 0, right?
Yes, definitely. If there's an eigenvalue of 0, then the matrix itself is what? It's singular.
It's singular. Okay.
Yes, and
okay,
if the matrix, yes, okay, so yeah, that was the easiest one to sort of throw out. Well, it was the most immediate because we're restricted by the examiner. So in which case the examiner had the power to mark any answer wrong. Not because it would be wrong, but because the student would have not followed instructions. Right. So the examiner goes on to then say, in part C, find elementary matrices E1 and E2 and a matrix U in row echelon form such that A is equal to this. Right. So let us analyze this question together. Right, let us analyze this particular question together and make sure we are very happy with it. So if we then say, find elementary matrices E1, E2, and a matrix U in echelon form, such that A equals E2, E1 times the upper triangular matrix. Okay, so in other words, we are attempting to factorize the matrix here. Okay, now obviously there are a couple of ways that we can use to attempt to factorize this matrix here. So if we're able to take the matrix A, right, and we have 6, 0, 0, we have 2, 0, 1, and we can actually be in a position to take this matrix and form from it what we call an augmented matrix. Right, so if you have 0, 0, 2, okay, this is the matrix A. But if we want to find the elementary matrices, so what do we do first? We actually take the matrix A and augment it. Okay. And then we have 2, 0, 1. I mean, there are many ways to do that. I've seen many people just putting the matrices adjacent each other for purposes of the elementary matrices. But now we can be able to do the, and then here you put 1, 0, 0, 0, 1, 0, 0, 0, 1. As if you're attempting to find the inverse, perform a series of elementary row operations. And then say, at this point, what do you then have?
We can multiply row 2
Yes.
by 3 and subtract that with row 1.
Yes, we can do exactly that part there. So, what then do it? Yes, okay. Right, obviously that is something we can do. So, and obviously at this point, we actually will be able to get a 0 here. Okay.
Yes.
So that would be one way to do that, to then say we can actually be in a position to get a 0 there. So what then can a student do? So there are a couple of ways to do that. So the first thing we can do is to actually attempt to multiply this one by 1/3. Okay, so one student can multiply this one by 1/3. Right, so if you multiply this one by 1/3, or you have this, okay, now if you have this, for example, this setup, what can you do in a way that will allow us to then immediately, right, immediately be able to achieve a 1, right, be able to achieve a 1. For example, if one wants to be able to achieve a 1, can we switch these rows here? Okay, that is one. There are too many ways to do that, which is what we can do. And that is what I'm going to do. Okay, so let us look at this very carefully. So if you take, for instance, this particular matrix, and you attempt to then say, can you switch rows? Right. And if you multiply this one by 2, right, you multiply this one by 2, and you actually, such that at this point, you perform subtraction. Okay, let's see. If you multiply this one by 2 or -2, or you multiply this one by 1/2, right? Okay, there are too many ways to do that. But let's just do this. Okay, I'm looking at the simplest way of doing this particular matrix so that we're able to actually achieve the result we want here. Right. What is the best way? Okay, let me just say, you have this one, we maintain it, and this one, we maintain it. Right, if we maintain this row entirely, and we maintain this row entirely, and we wish to perform a way that is going to transform this, how can we transform this particular row there, for example? How else can that be done? So we can attempt to do that. And how do we attempt to do that? So we can say row 3 plus what? Plus 2, row 2. Right.
But that's going to change the last, it's going to change the first value of the last row.
It's going to change the first value of the last row. What is it going to, okay.
Yes.
To say row 3 plus 2 of that, right, so what we're able to see that it's going to make this what? It's going to make this a 4.
4,
right?
yes.
And it's going to make this a what? It's going to make this a 0 still.
0.
And this is going to make this a what? It's going to make this a 4 as well. So it's going to actually produce a 4, 0, 4.
Right? Why 4? What's the row operation? Oh, yes, sorry. Yeah, that's right. That's right.
Yeah, okay, yeah. Okay, we're just plotting. We're just plotting. So in other words, it's gonna produce, for instance, a 404. Right now, a 404, is it ideal or not? And what else can we therefore be in a position to achieve with that? Because another student can come and then say, if you then want to do it differently, you can say row 1 or row 2 minus 1/3. Okay, let us just do that quickly because I'm just thinking of too many things here. Okay, multiply row 1 by 1/3. So 1/3
It's gonna be
row 1. Okay, it's gonna be what here? 2,
2,
0,
0,
0.
0.
Okay, and this one is gonna be 1/3, 0, 0. Okay, let's just do that only for now. And then have this one 2, 0, 1, 0, 1, 0, 0, 0, 2, 0, 0, 1. Okay, right. What have we done? We just multiplied the first row by 1/3. Okay, after we multiplied the first row by 1/3, what does this give us? And what can we achieve? Yeah, what else can we achieve with this? Can we be in a position to do something else, something different with it?
Subtract row 2 and row 1. But remember, we only need two matrices, two elementary matrices, and this is gonna give us like 3.
Yeah, that's the thing. So it's going to give us a little bit more matrices. Right. It's going to give us a little bit more matrices. Right. So what then would you suggest is the row operation at this point that one can use?
We can use the second row in the first row
We can use the
of
second row.
this.
Yes.
Yeah.
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 Mm-hmm.
So you can say
Row 2 plus 1/3. Okay. Okay. Now let's look at this. If, for example, okay, let me just make this one. Yeah, what do you think first before, because we can do many things. Yeah, I just want to change this so that we can reduce the number of the matrices we need. Right, so that we can reduce the number of the matrices we need. Right, you're thinking of something. What are you thinking?
So I was thinking
Yes.
we can say row 2
Yes.
equals to row 1 minus 3 row 2.
Okay, minus 3 row 2.
Row 1 minus 3 row 2.
Okay, row 1 minus 3 row 2. Yeah, okay.
Yes.
If we then say, okay, let's look at that. Row 1 minus 3 row 2. What is it going to produce? Let's just look at that together.
That's for the second row. That's the operation for the second.
Yes, okay. Yeah. But now again, you see, generally if we start with row 1, it must be an operation for row 1. Unless otherwise, obviously, you might have been taught differently. Okay.
No, it's the same thing.
Okay.
So it's going to give us 0
You
for
want
row
to
2.
okay, yes. So you want to apply it to row 2, right? So you're gonna get 0 here, you're gonna get another 0
0.
here, and you're gonna get a minus
Minus
3
3.
there. And then you're gonna get a what here?
1.
You're gonna get a 1 there. You're gonna get a minus 3 there. You're gonna get a 0. Well, you can always do that.
Yes.
Yeah. So what does this give? Okay, so obviously, I mean, you look at that and think about what this gives. And there are many ways to do that. But one of the methods we can use, because yeah, you can do that. And then this, when you get to this point, what you do, you multiply by minus 1/3. Will it not actually produce more matrices here?
Yeah.
Okay, I mean, you think about it, you think about it. Okay, right. So there are a couple of ways there are many schools of thought. But now if you look at this, let's just do this to cut the long story short. And I'm just taking this one as it is. Right, so you have this 0, 0, 1. All right, then let's look at this. I just want to use one method that will possibly make this a little bit easier. And obviously, see, there are too many ways to do this. And I'm just thinking, okay, right. Now, if you look at these and you want to achieve something, you can then say immediately row 2. If you take row 2 and you say row 2 plus 1/3 row 1. Right. So in which case, therefore, what would that give? Right. If you have 0, 0, 0, 1, 0, 0, and then you have row 2 plus 1/3 row 1. Right. So if you multiply this one by 1/3 and you actually add to this, it's going to produce a 4 here.
And to subtract.
Yeah. Obviously, you can always you later perform subtraction. Right. So at this point, if you get a 4 here, a 0 there, and obviously a 1 here, a 1/3, 1, 0. Right. And then you get 0, 0, 1, 0, 0, 2. Right. So, I mean, that is going to produce an elementary matrix here. Okay.
Yes.
Right. So if it gives you an elementary matrix, which is a possible elementary matrix, but now you can continue and perform another row operation. What other row operation can one produce here? Right. You can therefore attempt to sort of take also the original matrix. Okay, let us take the original matrix 6, 0, 0. Right, let me just remove this here. Okay, there's something I'm trying to achieve. So keep that elementary matrix and keep it. And yeah, definitely the one we just achieved. And now we're going to perform another row operation here. Right, so if we then say, right, if we then say, for example, you take the same matrix, A, 6, 0, 0, 2, 0, 1, 0, 0, 2, and you actually therefore are in a position to, okay, let's put this, the identity matrix here, and now perform the following operation. So you take this and you then say, row 3 plus 2, row 2. Okay, just observe what is going to happen here. Right, so y'all can just clean this up. And then now at this point, you have this one here, which is 6, 0, 0. Okay, row 1 is not going to be affected. Right, you're saying row 3 plus 2, row 2. Right, and that we are applying to row 3. So we're going to take 2, 0, 1, 0, 1, 0. Row 3 plus 2, row 2. Okay, so what is it going to produce? It's going to produce a 4, 0, 4, 0, 2, 1. Okay, let's just have this. Okay, yeah, just make that observation there. And now you have these two matrices that we've just got. And then now, simultaneously, when you get to this point, you actually therefore consider an upper triangular matrix. An upper triangular matrix that can be actually achieved out of this. So if you take the matrix A and you want to make it strictly upper triangular, right? So you can have the matrix A, which is exactly 6, 0, 0, 2, 0, 1, 0, 0, 2. Okay, you want to make it upper triangular, right? So you have right. So if you want to make it upper triangular, you need to reduce exactly the matrix A. So one way to reduce the matrix A straight away is to come to this matrix and say, because you want to remove this entry. Okay, you want to remove that entry. So how would you remove that entry, for example? So you can then say row 2 minus 1/3 row what? Minus 1/3 row 1. Okay. So if you have 6, 0, 0, and then you have 0, 0, 1, and
Why
then
is it one?
okay,
Oh,
yeah,
yeah, it's one.
yes,
Sorry,
it's 1. Okay, and then this one is going to be 0, 0, 2. That. All right, and then at this point, because this is a multiple of that, you need to subtract.
Yes.
Okay, so you'd have
yeah, now it works.
you can have row 3 minus row 2 minus
Minus
2,
two
yeah, whatever. Right, you can say minus 2 row 3, whatever. Yeah, yeah, that's sort of thinking out.
2 row 2.
Yes, well done. Minus 2 row 2. Correct. Well done.
Yes.
Right. So it's 6, 0, 0. And then if you have row 3 minus that, so this one is going to be 0, 0, 1. And then this one is going to be exactly 0, 0, 0. Okay. So this is sort of going to give us the upper triangular matrix, which is one triangular matrix. But now, if you then take those 3 instances we have got, I mean, you can always test these, and there are just too many ways to do this, but you can then be able to, let's test. If you then have, if you make the assertion that, therefore, that at this point, this one here is going to be your, matrix E1, and this one is going to be your matrix, elementary matrix 2, and then now be in a position to then say, you have elementary matrix 2 by 1 with you. You need to test this. What is elementary matrix 2? It's 1, 0, 0, 1/3, 1, 0, 0, 0, 1. Okay, you are trying to see E2. And then,
no, don't you start with,
yes?
do you start with that one, or do we start with the last row operation we did?
Okay, yeah, well, we're testing. We're testing.
Okay.
I hear you. We're testing. That is fine. So E1 would be 1. I know that obviously you can always, they have different ways. Okay, if we take E2, which is this one, and then E1, and then U, which is exactly this. I want us to multiply these and see what we're getting quickly. Okay, now let us multiply in any order. Which one is easier to multiply? Okay, these last two are easier to multiply. So you'd have 1, 0, 0, 1/3, 1, 0, 0, 0, 1. Okay, so let's multiply these two matrices. So this one is going to become what? 6.
6.
It's going to become what? 0. This one is going to become what? 0.
0.
Okay, and then this one is going to become what? 0.
0.
This is going to become what? 0. And this is going to become what? 1.
0.
Okay, and then you agree, right? Okay, and this one is going to become this by that.
Yes, yeah.
It's going to become another 0. This by that, another 0. This by that, another 0. Oh, right, and then let us squeeze some matrix here. So you multiply these by that, it's going to become a 6. This by that, it's going to become a 0. This by that, it's going to become a 0. And then if you multiply this by that, it's going to become what? It's going to become 2. This by that is going to become what? A 0. This by that is going to become what? A 1. You agree? Because this by that is 0, 1 by 1, etc. Okay,
1, yeah.
Yes. Multiply these by that is 0.
0,
These by that
0,
is 0. These by that is 0.
0. It is wrong.
Yeah,
So
so
I think
we need to switch. We need to switch something. There's something we need to do. Let me see what.
yeah, so we start with this
We
one,
need
the
to
one
start
in
with,
the middle,
we need to switch
the
E1
one with the
2. You
yes.
think we need to
We need
switch
to
these
switch.
two? Okay.
Yes.
Yeah, let's just switch the 2 and see what's
No,
going to
not
happen.
there. This is
Yes.
correct.
This is, let me see. What did we do here?
Yes.
Okay, let me
You
see.
have to switch that meter.
Uh-huh.
The first one and the second one, just swap
We
them
need to switch the
around.
first and the second one. Yeah, you
Yeah.
see, that is okay. Obviously, I mean, it's something small to be rectified there, because it's just this entry missing. Okay, just the bottom entry that we're missing. Okay, I'm just cleaning up the stuff because we're just missing this entry too, it appears. Okay. Let me see. Okay, right. So we have now again, we actually, yeah, because we need to one thing. I hope that one did not just make a mistake when multiplying the matrices themselves. Okay, let us check. Okay, now if we switch E2 and E1, that's what you actually were suggesting, right? So you suggest that we start with E1.
Yes.
Okay. 0, 1, 0, 0, 2, 1. And then E2. 1, 0, 0, 1, 30. Is that what you're suggesting?
Yes.
Okay. And then U is this one? 0, 0, 0, 0, 0, 1, 0, 0, 0. Let's just check what we're getting here. Right, which one is easy to multiply? Doesn't matter. Let's multiply the last two. So we're gonna keep 1, 0, 0, 0, 1, 0, 0, 2, 1. You multiply these with that, you get a 6. This with that, you get a 0. This with that, you get a 0. This with that,
2.
you get a 2. This with that is 0. This with that, a 1. This with that is 0. This with that is 0. Okay. This with okay, I need to just check. It's still the same. If well, I mean, something is going to work actually here, but we're very close. Just need to manipulate, provided we just are missing an entry somewhere. Okay, this with that is going to become a 6. Okay, let's just write this one a little bit towards the end. Right. Okay, let us see what. Yeah, but we're very close to actually, obviously, getting the result. Sorry. We multiply these with that, which is x. This with that, it's a 0. This with that, 0. Okay. Right. Which, because we want to produce the matrix A, so if you multiply these things, they must give us A. Okay. So so we multiplied it. We're getting the first row of A. And then now, if you multiply this with that, that's interesting. It's giving a 2, which is that. Okay. And then if you multiply this with that, it's a 0. This with that, it's exactly 1. Okay. We are getting the second row. And then, okay, but obviously you see, it's like it works. This with that, not quite. Not quite.
5.
Because if you
So
multiply
it's
this with that, what do we get? If you multiply this with that, this is
we
going
get
to
0.
be, this is going to be 4. So, but it must be 0. Okay, we're very close. Okay, it's just the bottom entry, but yeah, I think just switch this around. Let me just check again.
Where are you getting this from?
Please come again.
So where did you get 4?
If you multiply this row by this column, 0 by
Okay. Oh yeah.
by that. So, yeah, right. So, yeah, that is something that is very, very important. Okay, we need to just do a small switch, please. It's a small switch. Okay, yeah, but the answer is just in front of us. Yeah,
Yeah, we can move to the next question. I'll check it out.
yeah,
And then I'll see
yeah.
if I still get it wrong.
Yeah, that's the thing. Yeah, because you see now, you see. Let me just
Yeah.
take. Yeah, let me just take a second to just quickly check. Right, because I can't believe that. I mean, it has to work out. Let me see. All
Okay.
right, so if you have this one and this, okay, and then you have this and that and this, okay, and then now, if you are to multiply the matrix E2, which is actually 1, not naught. I'm wondering why this is okay, 1, 0. Okay, I'm just doing one quick check, and then we can always leave it. Okay, and then we can come back to it. Okay, right. Right. If this is exactly our E2, which is exactly this operation here. Right. And then now that is what we are actually able to have. Okay, right. So if you then multiply that with the matrix E1, which actually is exactly 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0 to 1. And then now we have this matrix we got here, which is exactly this. Okay, so it appears therefore that this matrix here, normally we can write it like this, but also this matrix you can write it as 6, 0, 0, 0, 0, 0. Normally we write the 0 row at the bottom, but you can write it either way. I mean, yeah.
That's another elementary matrix that you need.
Please come again.
If you swap that around, then it
Yes.
means you need another elementary matrix.
Yeah, that's the thing. So you need obviously another elementary matrix, because let me see if you have. Okay, let me just put. Let's just take it as it is. 6, 0, 0.
Okay.
Because I'm wondering why it's. I'm just trying to check why this is not giving us the result we want. Okay, because it's a small thing that must be. If we did not miss an entry here. Right. So, I mean, okay, let's just write the first one. I just want to examine the multiplication part of it. I'm sure that we'll just be able to get that right there. Okay, let me multiply the first two. Right, let me just multiply the first two matrices and then leave the last one. I'm trying to see why this. Okay, if you multiply this with that, what you get? You get a 1. You multiply this with that, we get a 0. You multiply these with that, you get a 0. Okay. You multiply these with that, you get 1/3. Okay. Yeah. You multiply these, you get 1/3. You multiply these with that.
You get 1.
Exactly 1. Thank you. These with that is 0.
You get a
These is a 0, right? Okay, good. These with that, it's a 0. These with that, it's a 2. Good. And then these with that, it's a 1. And then now I wanted to then write this one, 6, 0, 0, 0, 0, 1. Anyway, I made a mistake. This is 0 here. Okay, it's 0 here. Okay, and then it's 0, 0 here, like so. Right. So it's working. It's like it's working. Let me see. Okay, because I'm wondering why it's not working. Right, because I'm just wondering, yeah, it's like it's working now. Provided just want to see, because if you multiply out, maybe in the first multiplication there was a small error. You multiply this with that, you get a 6. This with that, you get a 0. This with that, you get a 0. Can find this with that, you get a 2. This with that, you get a 0. This with that, you get a
You
1.
get a 1.
So this with that, it's a 0.
0.
This with that, it's a 0. And this with that, it's a 2. So it's working.
Okay.
So it's working.
So what did you do?
Yeah, I was wondering where the mistake was committed, because it is exactly the matrix A we're getting. So that is what I'm wondering, maybe there was a small mistake in the multiplication, because I was wondering why it was not working.
No?
So yeah, so we
Does
actually,
the order matter?
please come
The
again, the
order in
order.
which you multiply.
Yes, the order in which you multiply matters, because you really can
So
see
maybe
that.
that's the problem.
Yeah, that was initially the issue, I'm sure. Okay, yeah, but this is the correct way to do it. But I'm sure that we shall spend a bit more time on these elementary matrices to make sure that we have very organized approaches in our next discussion. We need to see a bit more examples to make sure, because elementary matrices require you to maintain a given order, but you need to be very systematic in the way you deal with them. Okay, right. We shall spend a bit more time in our next discussion. So let us move on to the next thing. Otherwise, okay, let us see this one. Yeah. Okay. All right. So yeah, for each of the eigenvalues of A, which we got, find the eigenspace corresponding to that eigenvalue. Okay, so these eigenspaces are much, much easier. So let us find the eigenspaces. Now, eigenspaces themselves are obtained by using for each eigenvalue. Remember that we got that lambda was 0, lambda was 2, lambda was 6. Okay, so these
Yes.
are sort of the eigenvalues we got. Now, with this, then, let us start. For lambda equals 0, doesn't matter which one you start with. Right, for lambda equals 0, you remember the matrix we got, so it would be 6 minus lambda, 0, 0. And then you have 2 minus lambda. I'm just writing the general matrix, 0, 0, 2 minus lambda. And then now here you can write this one x, y, z, or anything, any variables that you have. Right, so, okay, right. So obviously if lambda is 0, we're going to plug 0 here in the place of lambda. So in which case we get 6, 0, 0, 2, 0, 1, 0, 0, 2, x, y, z. Right, 0, 0, 0. Okay, yeah, this is what we have. Now, if this is exactly what we have, what then do we do with this? We need to row reduce this. Okay, right. So if we can augment it, right, 0, 0, 2. Okay, I know that there are many, sometimes some people can just even ignore these zeros, this 0 column here. You have to see what method is used in your material there. Okay, right, but we want to reduce this matrix to the simplest possible. So what then can we do? Right, we can multiply this one by 1/6. Right, 1/6 row 1. Getting 1, 0,
Why don't you
0.
just take the one?
Please come again.
Okay. Well, I wanted to ask why aren't you just taking the one that we found in the previous question? Because it's
It's simpler.
in row echelon form. It's in
Yeah,
row echelon form. Or
yes,
do you want to
yes.
reduce it completely? It's
Yes, I want
fine.
to reduce it completely.
Okay, it's
Yeah,
fine. We
I
can
hear
just
you. I hear you. Yeah, we could do that. Okay, right. And then at this point, you have 2, 0, 1, 0. We could even, yeah, there are too many ways to do that. Okay, right. You can even multiply this one by 1/2 row 3. Doesn't matter.
0, 0,
Right,
1.
getting 0. Okay, let us see. Okay, once you get to this point, there are too many ways to do this one. Right, so we want to get a 0 here. You can say row 2 minus 2, row 1. Okay, so you have 1, 0, 0, 0. Okay, so this is going to be 0 because minus 2, row 1. Okay,
0.
1, that. Okay, so, and then we can have this one here. Okay, doesn't matter. In which case, therefore, you can achieve 0 here. Right, you can say row 3 minus row 2. Okay, 0, 0, 0, 0, 0. Okay, 0, 0, 1. Doesn't matter. Okay, I know you can really, you have freedom to write this the way you want. Right, then 1, 0, 0, 0. Okay, this is what we get. And this one is in reduced echelon form. Right, in which case, therefore, according to these variables here, so it's going to mean that x is 0 because of this, and this is going to mean that z is 0, and this will mean that y is free, and you can call it t.
Yeah.
Where t is in R. And this means that the x, y, z, and you see there are too many ways to do this, and you can always have shorter ways to do this in terms of the null. But anyway, this becomes null spaces. Okay, the x is 0, the y is t, the z is 0. Okay, so right, so it's 0, 1, 0. Okay, which is the null space. So obviously now for the W0, for 0, therefore, you'd be interested in finding the null space of the matrix A. Right, so the null space of the matrix A, which is this one. 6, 0, 0, 2, 0, 1, 0, 0, 2. Okay, so it is a null space of A. But in the end, then it is nothing other than, you can call the variable S or T, doesn't matter, but because it's a free variable. So now you have the 0, 1, 0. And this is true where the S itself is a real number. We can use T as well. Right. So this is exactly what we have. But now something that is very, very important is the fact that you need to minimize. Yes, do that for each one. Okay, but also need to minimize the amount of work. Okay. The next one is 2. Right, so obviously because you are training yourself to write under exam conditions. Okay, let me just write this trivial step here, but minus lambda. So you just subtract along the main diagonal the lambda. So you have 0, 0, 2 minus lambda. X, Y, Z. And then this one is 0, 0, 0. Okay, so, okay, now we're taking for lambda equals 2. Right, so, okay, so this is going to be exactly, if you subtract 2, it's going to be 4. Okay. Zero, 0. Okay, okay, just subtracting the 2 here. Yeah, so this would be 0, 0. Okay, so what we get here? 0, 0, 2 minus 2, 1. Yeah, any shortcut to this, but yeah, normally the best becomes row reduction to the reduced echelon form. In which case, therefore, yeah, because I mean, any other method becomes redundant, right? So at this point, you can multiply these by 1/4. Row 1, 1, 0, 0, 0. Right, so this one here, you can do whatever one likes. I don't like fractions, but you can multiply 1/2 row 2. Right, which means it's 1 minus 1, 1/2, 0, 0, 0, 0, 0. Okay, let's see here. What then do we have here? Okay, it doesn't matter what you do, but reduce the echelon form is what we desire. Sorry, now this one is already 1, 0, 0. So the first row is perfect. Here you have row 2 minus row 1, 0. And then this one is minus 1, 1/2, 0. 0, 0, 0, 0. Okay, so x is 0. All right, this is already in reduced ration form. So, and that would mean that this one is y. So y is all right. So yeah, we can do minus y equals minus that. Minus y equals minus that. So you can write y equals z out of 2. Z equals s, where s is in r. Okay, so which means therefore now you're gonna get the null space we want. So let us be brief here. We're gonna say W2 is the null space of the matrix A, 0, 0. And null space means it's 0. Null space means this. Means null space of the matrix A means AX is a 0 vector. This means the null space of A. So now null space obviously would be this matrix, right, would be this matrix there. Okay. Okay, I want to follow exactly the guidelines here. So obviously these are row equivalent, but now you'd have that 4. So you would gonna take 4. Yes. 4, 0, 0, 2 minus 2, 1, 0, 0, 0. Okay, that's because it corresponds with the null space of this. Right. So therefore that would be exactly what we achieve. And that has been row reduced to exactly this here. And that would mean that your x is what? So you can take s out, and then the x is going to be associated with 0, the first one. And then the y, it's going to be exactly, so now we have a choice, yeah? So because the y, yeah, okay, the y is z over 2. So the z over 2 now is going to be like 1/2. So you can make it 1 because you don't like fractions in the vector.
No, but that doesn't have s though.
Just
So
come
why are
again.
you writing it there? It doesn't have s. It's not a coefficient of s.
Yes, okay, but it is s over 2 because z is
Is
s.
that s over 2?
Well, it's z over 2,
Oh,
but z
it's
is
z.
s. Okay, let me write.
Oh, okay. Sorry. I didn't
okay.
see. Yeah,
Okay,
that's
that's fine.
confusing.
So it
I thought
is
it was
z.
7.
Okay, my apologies. So it is z over 2. But
Okay,
z
yeah.
is s. Okay, z is s.
Oh,
So
okay. Now
we can put 1/2 here, but
yeah, but
we have a choice. Okay, but we do not like fractions in the vectors. Okay,
yeah.
so because we do not like fractions in the vectors, there was supposed to be 1/2 here and then 1 here. I'm just writing this in a circle. So what do we do then if we have fractions and we factor out the fraction? Right, so the common method that is being used, so you could have 1/2, 1, 0. This vector is equivalent to what? So if you factor out the 1/2, it's going to be 2 here.
Okay.
Yeah, okay, so it's the same because you have the z over 2, which is 1/2, and this one is going to be 1 and 0. But you can factor out the 1/2, and that is what is also recommended in the books. Yeah, so they are row equivalent. So in which case, therefore, you can write like that, and this one here is as in the real numbers. So obviously that gives us the actual eigenspace associated with lambda equals 2. So lambda equals, the next one is 6. Right. So the lambda equals 6, we find the null space of this. So yeah, anyway, I'm just writing this formula here so that we're on the same page. Right. I know that it's maybe a very obvious formula. Right. So in which case, therefore, you'd have a 1 there, 0, 0, 2 minus lambda, and then x, y, z, and then 0, 0, 0. Okay, we're putting 6, 0, 0, 0, and then 0, 0 minus 4, y, z, 0, 0, 0. Okay, now it means therefore we're interested in the null space. But again, you see, the row reduction becomes necessary because I cannot imagine that anyone can claim that they can be able to see the solutions to this without the reduced original form. Okay, because you'd need, like we're doing, I know it's a bit tedious, right? But you need to reduce this. Row reduce this. Right, so at this point, you have the 0 there, which that this 0 is at the bottom. Okay, so we switch rows 1 and 2. Right, so which means therefore you would have 2 minus 6, 1. Okay. Let's switch row 1 and 2, and then again, because this 0 must be okay. It's
the bottom.
yes, at the bottom. Okay, this must be at the bottom. So it doesn't really matter. So okay, because we are moving in circles. I wanted us to, okay, let's multiply this one by minus that row 3. So you have 0, 1, 0, 0, 0. Okay, so in which case, therefore, you'd have this, but now you'd need 1/2. Okay, yeah, you'd need 1/2. Row 1. Okay, and then now you can switch row 3 and row 2. Whatever the thing. Okay, so doesn't really matter in the end. Right, normally we put the 0 at the bottom of the pack. Like so. Okay, now as we get to this point, then yeah, it's still possible to row reduce. Okay, so this is not in reduced form, in reduced Rachel form. We have row 1 minus 1/2 row 2. 1 minus that, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay, now this one is the simplest one in the what you call the reduced Rachel form, in which case, therefore, you have x equals 3y, z is not, right, and then y equals y, but you can call it s, where s is in the real numbers. Right, so with this, we are quickly able to write down what we want, and then we write W6, which is the null space of this one here. Right, so we take the null space of this one subtracted, or this one, right, which is the 0, 0, 0, 2 minus 6, 1, 0, 0 minus 4. Okay, which is exactly this one here, and then it is the null space of this matrix, and then it is multiplied. It is actually equivalent to, now let's come to this. So if this is the case, here you have, this one does not have fractions, so we can just take the numbers as they are. So for x, then we're gonna have a 3. For y, you're gonna have a 1. For z, we have a 0, such that s is an r. Okay, so this is sort of the stuff we're getting. We're good. We're good. Good. Now, this is exactly, okay, we got the null spaces and we're finishing pretty soon. For each of the eigenvalues of A, find, okay, it's the same question we answered, just made duplicates of the questions here. All right, is there an invertible matrix P such that this is a diagonal matrix D? If so, give P and D. If not, say why not. Okay, let's see. Okay, yeah, so obviously now the invertible matrix P, it's the matrix that contains what? That contains the eigenvectors. So at this point, the part of the eigenspaces. So for lambda equals 0. Okay, I'm just going to write for lambda equals 0, we got S 0, 1, 0. Okay, for lambda equals 0, we got 0, 1, 0. Right, so we got exactly 0, 1, 0, 0, 1, 0. Just writing this here. For lambda equals 2, we got 0, 1, 2. For lambda equals 3, 6. We got 3, 1, 0. Okay, so this is what we have. So now at this point with this, we are able to then say that the matrix P, right, so we write out this, so it's going to be first, we can write them in any order. So 0, 1, 0, but writing them in the order we obtained them, 0, 1, 2, and then 3, 1, 0. Okay, good. So this is the matrix P. Because we wrote the P like this, so is there an invertible matrix P? Yes, there is. So we can take P to be this, but you can also switch the columns around. And then D, okay, D, because we wrote this one is associated with lambda 0. Lambda, this one is the 0, 1, 2 is for lambda equals 2, and this one is for lambda equals 6. Because for lambda equals 6, we have the 3, 1, 0. So it means therefore
You take them
in the same order. Okay, good.
in the order of
In the order of the vectors. Okay, so because now the vectors for lambda equals 0, we put the vector first. Then we're going to put this lambda is equal to 0 here. Then the lambda equals 2, because it's for the second one, it's going to be here. The third vector is for lambda equals 6. We're going to have this. Then these things become zeros. Okay, and obviously because it becomes zeros, I know I'm just putting the big zeros like that. But now, in principle, you have these here. And then these are in the main diagonal. Okay, so obviously, you see, there are two matrices the examiner wanted. Is there matrix P? Yes, there is. It is this one. And a diagonal matrix D, and it is actually this diagonal matrix. But if a student switches them around, then the diagonal matrix is going to have these switched around. So give P and D. If not, say why not. Okay, good. So there is. Okay, good. Why? Okay, sometimes it's not there. Sometimes there's no matrix P. How do we know if there's no matrix P for in a question? Obviously, there's no matrix P in a question when the matrix is said to be defective. Right, there's certain matrices that are said to be defective matrices. So yeah, you can have those, but they're not very nice matrices. Defective matrices is when the geometric multiplicities and the algebraic multiplicities are different, because at this point the geometric multiplicity is the same as the algebraic multiplicity, because each vector, like the algebraic multiplicity of 0 is 0 because there's only one lambda equals 0 eigenvalue, but there's one vector for it. Lambda equals 2 is only one eigenvalue, one vector. Lambda equals 6 is only one value, eigenvalue, and one associated eigenvector. Because of that, this matrix is a nice matrix. Okay, it's not defective. There are certain matrices that are defective in the sense of you find that there are too many, the eigenvectors are too few. Okay, there are much fewer than the eigenvalues. And those matrices are not, you cannot have this property because here you don't repeat. These eigenvectors themselves are linearly independent by definition. Eigenvectors are linearly independent by definition. So you cannot have eigenvectors, you cannot repeat a vector here. So all these vectors are different. Because they're
Also,
so
when
different. Please come again.
we have the same, when we have the same eigen
Vectors.
vectors, like maybe let's say
Even the same eigenvalues.
the eigen.
Yeah.
Oh, okay. Also, let's say we had two sixes,
Yeah, 2 6s, then
then
you would need
it
two
was
vectors.
going to be impossible. Okay.
Okay, so if you had 2 6s, like lambda equals 6 and lambda equals 6, so that 6 occurs twice the eigenvalue, you would need
Yeah.
two vectors that are different.
Okay.
Okay, there's a situation where the vectors, there's one vector, but there are two eigenvalues that are the same. But there's one eigenvector in the eigenspace. So in that case, then the matrix P does not exist. Because that matrix
So
P is not invertible. Because the matrix P must be invertible. But now once there's one vector here, then it means that this matrix is going to have one vector short. If it's 3 by 3, it's going to have one vector short. If here you don't have two vectors, because for lambda equals 6, lambda equals 6, there are 2 6s, then you need two vectors that are, if there are two, then automatically they become linear independent and then they're going to work. Okay, so by definition, so let's look at the next question. Right. Just want to see what.
So you're saying that we should have distinct eigenvalues so that we can have the invertible matrix P.
Yes, but we still can have same eigenvalues, but the eigenvectors must be distinct.
The eigen what?
The
Vectors.
vectors. Yeah, but you see, the thing is, but what is the necessary condition? The necessary condition is that the geometric multiplicities and algebraic multiplicities must always be the same.
Okay.
What does it mean? It means that if you have two 6s, you need two vectors. If you have one eigenvalue, you need one eigenvalue, because otherwise then it's not going to work. Okay.
Okay.
Yeah. Right. So let's look at F now. For this matrix A, does there exist a positive integer k such that a to the power k is 0? The zero matrix. Justify your answer. Okay, let us analyze these together. So, for this matrix A, does there exist a positive integer such that this is the case, the zero matrix? So, this is a very, very interesting one. It's a very interesting one. We can always be in a position to, okay, from this fact. Okay, this is this. Is there invertible matrix P such that this is a diagonal matrix D? So it means P inverse AP is D. P inverse AP is what? Is D. Okay, so, but now if you use, you can write, because to raise this to a power, K, you need to solve for A here. So this P inverse, it becomes P, D, P inverse. Okay, yes. Yeah, so this P inverse, so in that order. All right, so, and with this then, because the matrix P exists, this means that A to the power K is going to be equal to P D to the power K P inverse. Okay, this is how we power the matrices. Okay, so these powers, that the K does not affect the P. Okay, so it's what we do. Right, so if the K does not affect the P, analyze this in line with this to then say, but the examiner is asking a question. Because obviously, because of that, does there exist a positive integer such that this is 0? a to the power k is 0. I mean, the argument would have to be that let's calculate this matrix and show that this matrix itself cannot be 0. If we assume that it is 0, we assume that because this a to the power k is equal to this. And if we force it to be equal to 0, we can argue that it is impossible. It leads to a contradiction, you know? And that is sort of the argument that we're going to do. So, and this is it. So suppose that a to the power k is 0. Since a is equal to this. Since a is equal to p d p inverse. Okay. This implies. Okay, implies that. So obviously we have, suppose a to the power k is 0, and we know that a is equal to this. Then we raise it to the power. And this implies that it implies that a to the power k, you can write this one, you know. It implies that a to the power k is p d k p inverse is equal to 0. Because if this a to the power k is 0, even this thing here is going to be equal to 0. Because a to the power k is 0. Okay. Now with this, then it then means therefore that we have p d to the power k p inverse is 0. Okay. So now with this then in mind, what does this mean? Okay, then we can solve for d to the power k by multiplying by the p inverse and the p. So you can multiply by p inverse p d to the power k, and then we have p inverse p is 0. Which is this one here is equal to 0.
Which is false.
Which is what? Which is false. Why would that be false? Because d to the power k, okay, I mean d to the power k equals 0 would mean, what is d itself? We wrote the d here.
It's 0, 0, I think.
You remember it, right? You remember it, and it is this one. It is 0, 0, 0, 2, 0, 0, 0, 6. Okay. 0, 0, 0, 0, 2, 0, 0, 0, 6. And then it is to the power what? It is to the power k equals 0. And to the power k equals 0, the k is just going to be on the diagonal things, entries. So it's going to be like this, and it's going to be 2 to the power k, and this is going to be 0, 0, 6 to the power k. And then it is equal to what? This is equal to 0. And with this, the question is, can this, because these are matrices, even this one must be a matrix here, and this is not just a number, it's a vector, right? So in the end, then clearly this is not the 0 matrix, because these are exponential numbers, exponential. So this would mean this is not 0, which implies therefore 2 to the power k is not 0. This and 6 to the power k is not 0. Okay. And because of this, okay, and which is a contradiction, right? Which is a contradiction because, right, which is a contradiction since this matrix D is not 0.
Yes, and then we try to show that it's 0, but it's not true.
Yes, yeah, definitely. Which is a contradiction. Which is a contradiction. Contradiction since d to the power k is not 0. It's not 0 for all k in the positive integers, the positive integer k. Right. And because of that, and obviously for this matrix, does there exist a case such that this is the case? So no, there is no such K. Right. So and you can put the conclusion here and then say
There's a contradiction.
yeah, definitely contradiction. Hence hence no such K exists. Okay, that concludes it. So right, because we've already said that there's a contradiction there. Hence no such K exists. Hence, no such K exists. No such K exists. Okay, no such K exists. And then we're done. Okay, so obviously, I mean, that would sort of be the answer to this one. We'll continue, obviously. I'm sure that we have gone a little bit beyond the time. We're supposed to stop it at 9, somewhat. Right. We actually will continue tomorrow.
Okay.
An advice on the time, but obviously there are certain things which I'll spend more time on, and that will do in detail, like your notion of the elementary matrices, in what you call something called LU decomposition, right? Because what that was something called the LU decomposition is what the expression was of the A in terms of the LU decomposition technique. So it's something which I'll spend a bit more time on, but there are also a lot of things on linear transformations that we're going to do, the kernels and the polynomial
Can we also focus on that linear transformations and inner products
and inner product spaces.
space?
Yes.
Yes.
Yeah, we're gonna spend time on that, and yeah, linear transformations in inner product spaces. We're gonna
Yeah,
spend time.
because elementary matrices don't
Yes.
really give me a problem. I can work that. I
Out quite.
can
Yeah,
do
they're
that on
not.
my own.
Yes,
Then,
yes, they're not. Yeah,
yeah.
but yes, I agree with you that obviously your inner product space and inner transformations remain very important for this course.
Mm,
And
yeah.
your spanning sets,
Spans, yes, exactly.
yeah, spanning
That's
sets, yeah,
big
and
thing.
things, yeah,
And
that's
bases.
and basis, yeah, and basis,
Yes.
yeah, finding basis for the span of the set, and so on and so forth. Okay, right. You're gonna
Yeah,
spend
can
a
we
bit more.
focus?
Yes, please come again.
Oh, can we focus on that tomorrow
Yes, we
when
shall
we
focus on
meet?
that tomorrow. Yeah, yeah,
Okay,
definitely.
no.
Right. We must thank you for joining us today. It was quite an interesting discussion, but I'm sure that tomorrow we shall have more to discuss. But yeah, we shall
Yeah.
actually go a bit more into detail, but we shall have more practice exercises as well. Okay.
Mm,
Right.
okay.
Yeah, we thank you for today. We're gonna send you the recording so that you can just obviously pass through and see what we actually had the chance to discuss today. Okay.
Okay, thank you.
Right. Thanks a lot and all the best. What time is suitable tomorrow? I don't know. What time would actually suit you best? Obviously, see, I know we have no focus in terms of how soon we need to finish, and we don't
Mm,
have any clear objective. Because we just started, but we don't know the
mm,
objective in terms of how many days we have, and how fast we need to get these wrapped up. But
yeah.
obviously, I would, yeah, so you'll think about it and maybe communicate, because now we are moving at the pace at the pace of one lesson at least per day so far.
Mm,
It is all
mm-hmm.
that we shall be in a position to cover these at least within the least amount of time. But obviously, I mean, I'm sure that you shall think of that and look at what is the projected time within which we need to sort of be done, and we need to have sort of exhausted. Once again, we have a projected number of 8 discussions
Mm,
that must be successive in an attempt to see how well we shall exhaust much of this content, All right, right.
because
Yes.
I have an exam on the 16th, so we should try do cover everything before then.
Yes, okay, yes.
Sorry?
Yeah, on the
Mm-hmm.
16th of July.
Yes.
All right, that's fine. And today it's only what date? Let me see. It's only the second.
It's the second, yeah.
Yeah. So we need to obviously, I mean, if we do at the rate of one lesson every week, it means that by
Every
approximately the ninth,
mm-hmm.
have covered approximately, would have had 8 discussions, you know.
Yes.
So,
Mm-hmm.
so it will be good enough, and we'll have a chance to reflect and see what's missing, what's not,
Okay.
what we need to emphasize. So yeah, so we're doing well. Okay, so yeah, our projected time will sort of balance up. All right.
Okay.
Yeah, I must thank you for today. We'll discuss again tomorrow. Once again, I was asking for the time that is suitable. I felt that the evening is best. Uh,
Okay, no problem.
yeah, I felt that the evening is best because the daytime might come up with a couple of other its own things. Okay,
Mm-hmm. So
right.
we can start at 6 p.m. tomorrow. 6
That's
is fine.
perfect. Yeah, 6 is okay.
Yeah.
All right. Thanks
Mm.
a lot, dear. Until tomorrow, take care. We shall send the recording in the next couple of minutes. Okay. So yeah,
Okay,
thanks,
thank
Ben.
you so
And have a
much.
good evening. Thanks. Goodbye.
Bye.
Bye.